We now seek to find the work supplied to a volume of fluid. In order to do this, let's consider a spherical volume with radius r prime, and r prime is not the same as r. That's the radius of a sphere that we considered so far, but in this case r prime is much greater than r. So it contains r, and it also contains the volume enclosing the sphere with the radius r, and the work W that is converted to heat is equal to W is the integral of tau, and this tau is the stress vector that we defined also in previous videos. You should check the videos related to the Navier Stokes equations. Dot product with the velocity times the element of the surface ds. We can also rewrite it by using components. We have xn u plus yn v plus zn w times ds. So this is just the dot product written out in all its components. So tau in this case is written as xn, yn, and zn. And in particular, tau contains the projection of the stress tensor that I will recall in a moment. It was defined in the videos on the Navier Stokes equations. Tau contains the components of the stress tensor projected on the normal to the surface. Why is that? Well, because remember the stress tensor was defined as the vector tau tensor product with the unit vector n. So we can also rewrite it by using tensor notation. Tij equal to tau I and j can be written as like that. From this expression we can also find that tau I is equal to Tij and j, where in this case we have to sum over j. If we sum over j, for example here, if we multiply by nj both terms, we have tau I and j, and we sum over j. When we sum over j, this is the unit vector, so that's equal to 1. And therefore, we get that tau is equal to the tensor t, and this tensor is applied to n. If you want, we take the dot product with n, but this is just matrix multiplication. It's a matrix multiplying a column vector. We can see that also as a dot product. So it's as if we were projecting the tensor t on the normal, let's say. And the components xn, yn, zn can be obtained from this expression, in particular from the components of the stress tensor, like this. So let's rewrite the stress tensor using this notation. I put a minus sign just for the sake of convenience, and then I will call its first column x xi, and then I have y xi, and then I have z xi. The second column will be x era, y era, z era. The third column will be x zeta, y zeta, z zeta, and this multiplies the normal, and the normal to a sphere can be written in this fashion. We have xi over rho, and this rho is defined as in the previous video, so it's the square root of xi squared plus era squared plus zeta squared. Then I have era over rho, and then I have zeta over rho, like this. And also from the videos on Navier Stokes equations, we found that this tensor is the stress tensor T tilde. I usually use tildes to denote tensors or matrices, but never mind. And minus t tilde, this tensor, minus this tensor can be written as P times the identity matrix, P is the pressure, minus 2K times the deformation tensor, which is also a tensor that we defined in previous videos on Navier Stokes equations. So this is the deformation tensor. And if we write this using components, we get also, if you go back and check those videos on this tensor, you will find that there is something more in this relation, but since the divergence of the velocity is zero, it means that the fluid is incompressible, and this expression will simplify. Anyway, this tensor can be written as, so the first element, the one element is P minus 2K derivative of U with respect to xi. Then this second entry, the entry that is on the first row and the second column is minus K du d era plus dv d xi. Then the entry that I have on the first row and the last column, the third column, is minus K du d zeta plus dw d xi. Then the two entries, so the entry that we have on the second row and the second column is P minus 2K dv d era. Then the entry that we have on the second row and the third column is minus K dw d era plus dv d zeta. Then the entry that we have on the third row and the third column is P minus 2K dw with respect to zeta. And the part that we have below the diagonal is simply symmetric. So this tensor is symmetric, and therefore we just need these 6 components that I have written down here. And therefore, if you equate the components of this tensor minus t, so you just have to change the sign here if you want to equate this tensor to this tensor here, but we also have a minus, so it means that essentially x xi will be equal to this and x era will be equal to this, and so on and so forth. You get the idea. So let me write it here. We have x xi equal to P minus 2K du over dxi, y era is equal to P minus 2K dv d era. Then we have z zeta equal to P minus 2K dw d zeta. Then we have x era equal to y xi equal to minus K du d era plus dv d xi. X zeta is equal to z xi equal to minus K du d zeta plus dw d xi. Then we have y zeta equal to z era equal to minus K dw over d era plus dv d zeta. And the expressions for u, v, and w become simpler if we take into account that for rho equal to r prime, the terms of higher order can be neglected. So now that we have taken a look at these stresses, these stress components here, we also need to rewrite the components of the velocity, because this is what we want to calculate. Okay, so xn, yn, zn can be obtained from this formula here. In particular, you can see that xn is related to x xi, x era, x zeta, because we have to multiply this row by this column. And if we get these three components, which can be obtained from these relations that you find here, you have x xi, x era, x zeta, and they can be calculated because we have found u, v, and w, right? So we just have to calculate these derivatives and then substitute these expressions. And then we also have, of course, xi and rho. I mean, those are just functions. We have to integrate over those functions. And in principle, we can do all of this. So I will not do all the algebra to obtain the final expressions. I will just lay out the most important, let's say, steps to be taken, and then we will get to the result without doing all the algebra. It is just algebra. There is nothing important about it. But anyway, as I said, also the expressions for u, v, and w that we obtained earlier can be simplified a little bit, because for rho equal to r prime, and since we know that r prime is much larger than r, the terms of higher order can be neglected. So if we go back and take a look at the expressions for u, v, and w that I have written here, we can simplify some terms. In particular, we can simplify this term here, because you can see that there is a higher power of r over rho. In this case here we have the power r cubed over rho to the fifth, but if you want you can put rho squared out here, because you can see that this term is also proportional to rho squared if you want. It is of the same order as rho squared. It behaves as rho squared. And here of course we have a term which is proportional to r over rho to the third power, whereas here we have r over rho to the fifth power. So this can be neglected, and also this one can be neglected, and therefore also this one, this one, this one, and this one. So we can simplify these expressions, and let me rewrite them below just for the sake of convenience. We have u approximately equal to a xi minus a xi squared plus b eta squared plus c zeta squared xi 5 over 2 r cubed over rho to the fifth power, v approximately equal to b eta minus a xi squared plus b eta squared plus c zeta squared times eta times 5 over 2 r cubed over rho to the fifth power. Then we have w approximately equal to c zeta minus a xi squared plus b eta squared plus c zeta squared. This multiplies zeta. Then we have 5 over 2 r cubed over rho to the fifth power. And also p can be rewritten. So remember the expression for p. Let me go back and show you the expression for p. This is the expression for p, where we can also substitute the derivatives here because we can calculate them. We have calculated them in previous videos. So if we go down and substitute those derivatives, we have p equal to minus 5 over 3 r cubed k. This multiplies a times minus 1 over rho cubed plus 3 xi squared over rho to the fifth power plus b times minus 1 over rho cubed plus 3 eta squared over rho to the fifth plus c times minus 1 over rho squared plus 3 zeta squared over rho to the fifth, like this. And then when you sum these three parts, so this term, and this term, you will get 0 because a plus b plus c is equal to 0. So you can rewrite the expression like this. You have minus 5 r cubed k over rho to the fifth times a xi squared plus b era squared plus c zeta squared, like this. This is the expression for pressure. Now we have all the formulas to calculate xn, yn, and zn. So xn is equal to minus x xi over rho plus x era over rho plus x zeta over rho, which simply comes from the multiplication between, where is it, this row and this column in order to obtain xn, as I said earlier. So we can calculate xn, and I'm not going to do the algebra here, so I'm going to skip this algebra because it is very straightforward. It's just algebra. You just have to substitute some expressions and carry out some computations. It is nothing major. It can be done also quite quickly. It's quite boring, but it can be done quite quickly. And the expression that you will obtain is the following. We have 2ak xi over rho minus 5ak xi r cubed over rho to the fourth power plus 20 r cubed k xi over rho to the sixth power times a xi squared plus b eta squared plus c zeta squared, and this is the expression for xn. Let me write it like this. This is xn, and similarly you can also calculate yn and zn. Let me write down these expressions. We have yn equal to 2bk eta over rho minus 5bk eta r cubed over rho to the fourth plus 20 r cubed k eta over rho to the sixth power times a xi squared plus b eta squared plus c zeta squared. So you can simply obtain the expression for yn from xn, and you just have to use symmetry in order to obtain, because for example in this first term I have simply substituted a with b and xi with eta, and similarly for the other terms. Then you also have zn, which is equal to 2ck zeta over rho minus 5ck zeta r cubed over rho to the fourth power plus 20 r cubed k zeta over rho to the sixth power times a xi squared plus b eta squared plus c zeta squared, like this. Now we can use these expressions in the calculation of xn times u plus yn times v plus zn times w. And you simply use these three equations and also the equations for u, v, and w, the simplified version. These three versions here, where we neglect high order terms, and what you get is the following. I'm going to rewrite it here because otherwise I might not have enough space. 2k over rho. So there are some algebraic steps here. I'm not going to do the algebra. As I said, it is useless because, it is just basic algebra. You just have to do some computations. And here we have 2k over rho times a squared xi squared plus b squared eta squared plus c squared zeta squared minus 5r cubed k over rho to the fourth times a squared xi squared plus b squared eta squared plus c squared zeta squared plus, and I'm going below here, plus 15 k r cubed divided by rho to the 6th power, and then we have a xi squared plus b eta squared plus c zeta squared plus higher order terms. We'll neglect higher order terms, and then we have to integrate now this expression, this complicated expression, but it's complicated only because it is quite long. But the integral will be very easy to calculate. Actually, we have a set of integrals because you can see that we have to integrate this over the surface, which is a sphere of radius r prime, and the terms that we have to integrate are simply xi squared, eta squared, zeta squared, these ones, and also this one, this one, this one, and also these terms here. That's a square. Because rho on the sphere will be a constant, and it will be equal to r prime. So the integrals that we have to carry out are of the following form. We have the integral of xi squared ds, which is equal to integral from 0 to 2 pi, integral from 0 to pi of r prime squared, cosine squared theta, sine squared phi. So I have simply rewritten this component, which is the x component if you want. The xi component goes along x, written using spherical coordinates, where theta is a variable which goes from 0 to 2 pi, so it's defined on the xy plane, whereas phi is an angle measured from the z-axis, and it goes from 0 to pi. So if we move on, here we have the Jacobian of the transformation, which is r prime squared sine phi, and then we have d phi, d theta. And this can be written as, so we can also do the calculation here for the first one. This is simply equal to r prime to the 4th, integral from 0 to 2 pi, cosine squared theta, d theta, which is just pi. Then we have integral from 0 to pi, sine cubed phi, d phi, and this is equal to 4 over 3 pi r prime to the 4th, which is equal to integral eta squared ds, which is equal to integral zeta squared ds, just for symmetry reasons. And then similarly, we also have to calculate other terms, so other integrals. For example, we have, let me do it below, integrals of this kind. We have integral xi to the 4th power ds, which is equal to integral eta to the 4th power ds, which is equal to integral zeta to the 4th power ds, which is just equal to integral from 0 to pi, integral from 0 to pi, r prime to the 4th, cosine to the 4th phi, times r prime squared, times sine phi, d phi d theta, which is equal to 2 pi r to the 6th power, integral from 0 to pi of minus cosine to the 4th power phi d cosine phi equal to 4 over 5 pi r prime to the 6th power. And then there are also integrals like this. For example, we have integral eta squared xi squared ds, because remember that in the expression inside our integral above, we also have something like this. We have a xi squared plus b eta squared plus c zeta squared squared. So we will also have such integrals, and they can be carried out easily. I will not do the integration. This is also equal to integral of xi squared zeta squared ds, which is also equal to integral zeta squared eta squared ds. And if you do the calculation, you will get that this is equal to 4 over 15 pi r prime to the 6th power. And by doing the calculation for the work, so work is equal to the integral of xn u plus yn v plus zn w, which is an expression that we wrote above, and we have to integrate over ds. The final result can be written in this form. It is 2k delta squared times v plus phi over 2, where delta squared is simply equal to a squared plus b squared plus c squared, whereas phi is the volume of the sphere with radius r, so 4 over 3 pi r cubed. So we have r, not r prime, and then v is the volume of the sphere with radius r prime, so 4 over 3 pi r prime cubed. And v is much larger than phi because r prime is much larger than r. After this, Einstein also considers the case where there is not just one sphere, but we have n spheres with radius r. He finds some similar expressions also in that case because it is more important, because in general inside our fluid there can be multiple small particles, and we will address this issue in the next video.